Hello, ladies and gentlemen, and welcome to the third lesson in the 3D Buzz Math VTM series. My name is Zach Parrish, also known as Dark Viper 338 on 3dbuzz.com, and with me tonight is my good friend, Mr.
Rob Rolnick, known on 3dbuzz.com simply as Demondo.
Yes, and if you are completely new to this series or would like to know more about the free VTMs that 3D Buzz gives away, head on over to 3dbuzz.com and check out our nightly radio show that we play, record, I guess you could say, Monday through Thursday, 4 times a week, and you can download those from the BuzzNet radio link at the top of the page. Now, tonight, we are going to take the lesson that we had earlier, lesson number 2, and we're going to expand upon it, and Mr. Demondo, as usual, is going to be our guide in the wonderful world of matrices. So, Demondo, why don't you talk about what we're going to be discussing tonight?
Well, tonight we're going to be talking about 2 methods that add to the previous methods we discussed for solving systems of linear equations.
Cool.
I find that when you're dealing with more than 2 variables, so 3, 4, 17, these methods happen to work a lot nicer.
Gotcha. Cool.
So, systems of linear equations, part 2. Like I said, if you're dealing with more than 2 variables, then these methods work nicer, they're cleaner, and I find they also work very quickly.
Absolutely. If you work through the problems at the end of the last video, you might have seen that some of them get into using more than just 2 variables.
Yeah, there were some with x, y's, and z's.
Yeah, which you can solve using the methods that we covered earlier. It just gets a bit more lengthy. So in this video, we're going to show you some ways to simplify that a bit.
Right. It should be noted that although these methods are quicker, they still require a bit of, scratch paper to work on. They're not exactly short, but no method is. And it should be noted that the notation used throughout this lesson is my personal notation that I like to use. It's not necessarily the most recognized or the notation your teacher might use.
Okay, cool.
Anyway, matrices provide a standardized technique for solving systems of linear equations. 2 common techniques are Gaussian elimination and Cramer's rule, both of which we will be discussing in this lesson.
Awesome.
So, first we should get into how to set up your matrix. Well, what a matrix is, you can think of it kind of like, cubbies or like a grid.
Okay.
And each box, if you consider each of these in a box, would be where you put a number. So, in a 3x3 matrix, like this one, this part here, you'll notice there's 3 entries by 3 entries, so 9 entries total.
Right.
If you look, the numbers 3, 2, 1 correspond to the coefficients of your systems of linear equations.
They do indeed.
So 3x plus 2y plus z is 3, 2, 1. And then equals 1 is that 1 right here. This vertical line is used to distinguish between your coefficient half of the matrix and your solution half.
Gotcha. It's kind of like your equal sign.
Exactly. So if you had, let's say, 2x plus y minus 1, it would be 2, 1, minus 1, and then 2. And so on and so forth for the third.
Awesome. Now, how does this help you out?
Well, when working with matrices, there are 3 main operations that you can do. These are the primary matrix operations. There are others, of course, but these are the ones we'll be discussing in this lesson. You can add 2 rows, multiply a row by a constant, or switch 2 rows. Okay. So essentially, these are the same operations you'd be doing when you were using the earlier add and eliminate technique.
Sure. So it's just a way to nullify a certain variable.
Right. Except this keeps it very organized in one little contained unit. You don't write the x's, the y's, and the z's all the time, etc., etc. And it looks a whole lot nicer when working.
A little easier to follow.
Right.
Cool.
So anyway, we'll just cover these operations pretty quickly. Adding 2 rows. Well, that's pretty simple. We have 2 matrices, these 2. And this is pre-operation and post-operation. So this is the matrix we set up, I think, 2 slides ago. And if we wanted to add row 1 applied to row 2.
Now, why would we be doing that?
Okay. Well, remember in the previous lesson where we talked about you'd try, I think we got rid of the y.
Yeah.
Using adding 2 equations.
Indeed.
This is the same technique, but if you remember, the first column was all the x's.
Right.
Second column was all the y's, and the third column was all the z's. Well, if you look here, by adding row 1 to row 2, we eliminated a z.
Yeah, very cool. So the point is, you notice that between rows 1 and 2, if you were to add them together, you would get rid of that z. You'd zero it out. Right,
and if you would say, let's say here, I'm not going to do it, well, it's not done. I guess I could jump to Photoshop and do it if you'd like as the student. But if we'd go row 3 minus row 1 applied to row 3, so row 3 would be underlined, you also get rid of the z.
I gotcha.
And then these two rows, second and third, at that point, after you did that subtraction, would only be dealing in two variables, x and y.
Sure.
Okay.
So before we have the operation here where we're going to add rows 1 and 2, we have the original matrix, thank you, up here. We don't have the pen tool out. Let's go ahead and get that so we can draw, because I love drawing. So here's our original matrix, and then after we add rows 1 and 2, we end up with this matrix.
Right, and as
We've applied that to row 2.
Right, because I underlined just for my notation's sake. Other people have different conventions.
Sure.
I find that works really clear when you're reading over it fast.
Gotcha.
In any case, when you're adding, all you do is you go entry by entry and add. So here, if you're for the first entry, you go row 2 plus row 1, so that's 2 plus 3, and you got 5. Here you'd go 1 plus 2, because you have a 1 up here and a 2 right there.
Right. No, they probably can't see your pointer.
So you've got a 1 and, let's say here, we've got a 1 and a 2.
Oh, look at you go.
And you add them, and you get a 3, and you place that in row 2, because it's applied to row 2. And then when you add the 1 and the minus 1 in the next column, you get a 0. And finally here, if you add the 1 and the 2, again you'll get 3, because it doesn't matter if you add 1 and 2 or 2 and 1. And that gets in the final, in the solution column.
Cool.
So essentially what you now have, which technically it isn't telling you anything you didn't know before, it's just cleaner, says that 5x plus 3y is 3. Where it might not have been obvious prior.
Sure.
Okay, so the second operation is multiplying a row by a constant. Now, this is generally used to... So first I'll explain how it works, and then I'll explain why it's used.
Okay, cool.
It might be cleaner. It might be easier to understand that way. So here we did 3 times row 3. So similar to before, you go entry by entry and multiply by 3. So 2 times 3 is 6, because it's originally a 2.
Right.
Now it's a 6. 1 times 3 is 3, 1 times 3 is 3, and 3 times 3 is 9.
Okay.
And the reason you do this is, let's say you had another... Actually, here. Let's say that this last entry was minus 3. It's not, but let's just say it was minus 3. So I'm turning that into a 3 suddenly.
Wow, that's
look at
clever.
that.
Yeah, look
minus
at
3 now. And now, by doing that, we can add row 3 to row 2, apply to row 2.
Thereby nullify the x.
Right.
So the point here is that you can take these methods, the adding of 2 rows and the multiplying by constants, and start combining them to start narrowing down your selection.
Right. Frequently, you'll see someone do the 2 steps in one operation. It would say something like row 1 plus, I don't know, 3 halves, or I guess that should have been a minus, but oh well, row 2. So you'll have row 1 plus 3 halves row 2, and it should have been a minus, so I guess I can fix that quickly. Eraser. Just nuke the plus, and now it's a minus.
There you go.
And that way, now you get rid of the first entry, I believe.
Yeah, I'm with you.
And
very cool.
That way you did the 2 steps in one. The important thing to realize is that you multiply each entry, and when you're doing it, you don't just multiply a single one.
Yeah, absolutely.
Okay, so grabbing back the felt tip pen tool before we forget, we'll jump to the next slide. Switching to rows. Switching to rows technically doesn't really change anything, nor does it really appear at first to have any use. Because all you're doing is you're saying whatever's in row 1 now goes, well, in this case, whatever's in row 1 gets switched with whatever's in row 3 and vice versa.
Sure, you just flip them.
Right, so here row 3 was 2, 1, 1, 3. Now that's row 1, 2, 1, 1, 3. And row 1, which was originally 3, 2, 1, 1, becomes 3, 2, 1, 1.
And this is primarily an organizational method.
Right, so the goal, I should say, I'll take a quick detour, is to say that you're trying to get something that looks like this, using these 3 methods. 1, 1, 1, 0, 0.
There you are, not
0.
using that Wacom tablet again.
0. No, I'm not.
I mean, those zeros look like they've just been beaten to death.
Yeah, well, I'm an evil person. Now, if you can get that, and whatever would be in the final column here, I kind of left that out. We'll have 3 numbers here, so value.
So it'd be like
value.
The first row would handle X, the second would handle Y, the third would handle Z.
Exactly. You'd have X plus 0Y plus 0Z is something.
So switching rows is just a way that you can adjust your rows to follow that guideline.
Right, so it becomes very clear.
Yeah.
In any case, Gaussian elimination is set up in a very specific way. You're using these 3 previous steps to get this matrix down here, this one. It's Gaussian elimination is, like I say in the points, it's an advanced form of the add and eliminate technique. it requires a bit of room for working, as you can imagine. You're writing out the matrix every single time after every single step.
Most things do.
But when you get a matrix like this, you know clearly that Z is equal to something.
Sure. You figured that out at that point.
Once you know Z, then this right here now is a constant, because you know whatever Z is.
So you just plug it in, and then you figure out
and
Y.
And then Y is pretty obvious.
Gotcha.
And once you know Z and Y, the top row is also pretty obvious.
Right. Excellent.
But like the final point says, if you wanted, you could continue further too, which basically means you can solve so that you had the method I showed in the previous slide where it's pretty clear X is this, Y is this, Z is this, and then you don't even need to do that.
Are you planning on giving us an example of that?
No, I was planning on making the students panic and, go, oh my god, we just learned a lot.
Oh, okay.
No, I'm just
All right,
kidding.
cool.
So I'm going to jump into Photoshop real quick.
Show me.
And I have a matrix in mind that I'll use, and we'll solve this one. So this is our matrix.
Oh, you see how much cleaner it is when you use the Wacom tablet?
Yeah, oh well. 1, 2, 3.
That's beautiful, man.
3. 4, 5, 6, 6.
Oh, man, that looks like a rough matrix.
Sorry, I didn't have enough room.
Are you cleaning it up?
That's still a 4.
Yeah, it looked like goalposts for a minute.
Yeah, I'm a big football fan.
Yeah.
7, 8, 8, 2.
All right.
So basically what this is saying is, like before, the first column is X, second column is Y, third column is Z.
Sure.
And the final column is your answers.
Okay, you're Canadian. Do you say Z or Z?
I interchange.
Yeah, I do too. All right, never mind.
In any case, so essentially row 2 is saying 4X plus 5Y plus 6Z is 6.
Sure.
And so on and so forth for the other two rows. So we're going to start by adding row 1, or rather, we'll say row 2, applied to row 2, minus 4 row 1. And at the same time, I might as well do it at the same time, row 3 minus 7 row 1.
Ooh, so now you're getting fancy.
Well, the concept is by doing these two steps, we'll get rid of the 4 and the 7.
Right.
And we'll be left with X's and Y's for the second two rows.
So how does that first part work
Well,
with the R2 minus 4 row 1?
Well, first I'm just going to rewrite row 1 because that's not changing.
Yeah.
The important thing is if you're doing two steps at once, that since I'm using row 1 as the row I'm using to apply the operation, it's fine because row 1 isn't changing.
Okay.
I couldn't say something like row 2 plus row 1 apply to row 1. I could. I'll write it and then I'll say.
Okay. Well, hang on. Let's be democratic about this. Let's ask the audience: do they think that we should do two steps at once, or should we just go one step at a time?
Don't say anything if you want to. I heard nothing.
No, I heard several people distinctly say they want us to go one step at a time, at least the first time through it.
Okay, fine.
You just got to listen up. See, I know how to listen for these people.
Okay, so we'll start with. You know what? Zach's right. He heard the audience. I didn't. I'll erase this part.
It just might make it easier the first time we go through it. Then if you want to show people how to start combining steps, that could be really cool.
Okay, so anyway, 7, 8, 8, 2. Again, that row is not changing.
Okay.
So the only row that's changing is the second one. So 4 minus 4 times 1.
Right.
So 4 minus 4 times 1.
So you're taking row 1, you're multiplying it by 4 and subtracting that from row 2.
This was what was in row 1 and that was in row 2 for the first entry.
I gotcha.
That gives 0. Because that was what our intention was.
Exactly.
So that's 0. Then we have 5 minus 4 times 2. That equals negative 3, I believe. So that's a negative 3. And we have 6 minus 4 times 3, which equals negative 6. And finally, 6 minus 4 times 3, which also gives negative 6.
Gotcha.
So that negative 6 was kind of off. It should be closer to there-ish, but I'll leave it.
It's okay.
We
can still see it. We're about to draw another matrix anyways.
Right. So now I'll just erase not the matrix, but the work, because I need to write beside it.
Right.
So the matrix stays, and this gets kind of erased.
Okay.
And now we want to get rid of the 7 over here. We want to get rid of that 7. So we go row 3 minus 7 row 1. And you'll get 1, 2, 3, 3. That doesn't change.
Right.
0, negative 3.
Negative 6.
Negative 6, negative 6.
Gotcha.
Now, we know this is going to be 0. That was our intention.
Sure.
So that goes 0. And now we say, okay, close that.
And the reason you ended up with 0 is because you took the value in x from row 1, you multiplied it by 7,
Right.
and applied it down below. So you ended up with negative 7.
Right, so
And which went
7
down to
minus
0.
7
Right.
equals 0.
Equals 0. There you go.
Okay, so now we have 8
Mm-hmm.
minus 7 times
2.
2
Which is
equals,
14.
well, 14, right?
Yeah,
And 8 minus 14 is negative 6.
There you go. Groovy.
So that's a negative 6.
Mm-hmm.
And we do it again. So we have 8 minus 7 times 3 equals 21. 8 minus 21, I believe, is negative 13.
Sounds good. We'll go with it.
I think that's right.
No, it's right. You're good.
And finally, we have 2
Yeah.
minus 7 times 3 equals negative 19.
Mm-hmm. Awesome.
So, negative 19.
So we're getting there.
We're getting there. So as you can see now, in this new matrix, this kind of dilapidated matrix, we now have no x's in the final 2 rows.
Right.
And the final 2 rows are only dealing with systems of linear equations dealing in x and y.
Sure.
So, we'll draw a nice big vertical line, or almost vertical line,
Close enough.
and we'll start working here. And like before, I'll erase the works so I can write beside the matrix.
Okay.
Okay. So the next step is to, let's think. The next step that I'd like to do is to...
Clear out the y in the third row.
I'll clear out the negatives in the third row. I'll
Okay.
go, I'll do the in the third row or second row. I think I'll do it in the second row.
Okay. Okay.
Because I'll go negative 1/3, row 2. Just do a bit more
You're
erasing. 'Cause
multiplying all of them by the same value.
yeah, negative 1/3. The goal in doing this is that I want this term to be a 1.
Yep.
This one right here.
Yep.
And,
Which will turn the second one into 2.
right, and this will also become 2.
Yep.
So, doing that, we get this. 1, 2, 3, 3.
Mm-hmm.
0,
1,
1, 2, 2. And 0, negative 6, negative 13. Make that
Yeah,
go like
okay.
that.
I'm with you.
Negative 19.
Yeah. Cool.
Okay. So now, we can go, I guess we can, add, we'll go row 2.
Mm-hmm.
So we'll go row 1, apply to row 1, minus 2, row 2. So that we can get this term to be a 0.
Okay.
So I assume the audience is catching on to what we're doing.
Yeah, you kind of jump around a lot. You have to, and it requires a lot of writing, so you just got to get used to it.
Right, so 3 minus 4 is negative 1.
Sure.
And then, again, 3 minus 4 is negative 1.
Mm-hmm.
Row 2 doesn't change, and row 3 doesn't change. So, there you go.
So now you want to go ahead and get rid of that negative 1 up there on row 1?
This one? Not just yet.
Okay.
I'm just gonna
I'm jumping the gun. That's what I do.
slide that over a little.
Wow.
So we have more room to work.
Yes, bring your scratch paper along when you're doing this on your own.
Right. Okay. So, with that done, I guess the next step is to go add row...
You still got your move tool out.
Oops.
Yeah.
Pen
There you
tool.
go. That's the one.
So I want to go applied to row 3.
Mm-hmm.
I want to add row 2 6 times.
Okay. 6 times row 2.
So, now we have 1, 0, minus 1, 1.
Row 1 doesn't change.
Exactly. Row 2 doesn't change.
Row 2 doesn't change.
And now we work out what row 3 is going to be.
Which would be 0, 0, and negative 1.
Right.
There we go. I think that's right.
That is right. And this becomes, I think it's 14. Oh, negative 7. Negative 7, not 14. Don't know where 14 came from. Took the answer, multiplied it by negative 2. Okay, so we're almost done. if you remember, Gaussian elimination wanted these to be 1s and didn't care what all this was.
Mm-hmm.
Well, it didn't even want these to be 1s. These could be anything, but I like having them 1s.
It's just cleaner.
It's cleaner. So now all you have to do is go -1, so minus row 3.
Gotcha.
And you get something really nice, which is 1, 0, -1, 0, 1, 2, 0, 0, 1. And fear the messy handwriting, -1, 2, 7.
Gotcha.
So, looking at this, it's pretty clear what Z is. I think.
It's going to be 7.
Yeah, exactly.
It has to be.
Right, by our setup, because we know the third column is Z, and 0x plus 0y plus Z is 7.
So we could theoretically solve this whole thing.
Right, well, we can just plug that. We know 2Z is going to be 14.
Right.
And solve for y. And we know minus Z is going to be -7 and solve for x. But that would require breaking out of matrices. I'm going to keep the matrices and solve for it slightly differently.
Okay.
I'm going to do these two in one step because I think the audience is kind of getting bored.
Okay, that's cool.
I'm going to go row 1, apply to row 1, plus row 3. And
now you're getting fancy.
Row 2, apply to row 2, minus 2 row 3. And if you do all that, you'll get this. 1, 1, 1, 0, 0, 0, 0, 0, 0. I kind of jumped around, but that's because that was what... Oh, wait.
Wow,
that was a mistake.
that's like the messiest matrix you've done yet.
Yeah, I think I'll erase it and write it neater.
Wow, I'm impressed.
Oh, I can get a lot messier
That looks almost
than
like a TV remote control.
1, 0, 0. And these are zeros by what we wanted. So it looks kind of like this. That's our final. So now we know x is something, y is something, and z is something.
Right. So we should just have the values over here on the other
side. Right. So that's 7. If you work it out, this is going to be, I believe, minus 12. And the top one is going to be 6.
And if you followed what we've been talking about so far, you should be able to handle that last step, even if you don't combine them. You should be able to do that on a piece of paper, just kind of following what we did. You just start off by taking row 1 and applying to it, row 3? On this first step here?
Yeah, that's row 3, because row 3 is just Z, and we want to get rid of the Z term.
Right, and then after you were done with that, you would take apply to row 2, twice row 3, and then you'd be done.
Right.
Doing exactly what we did earlier.
Right, and the reason you can do it in one move and not do it and break it down to 2 steps is because row 3 is not changing.
Right.
So there's no confusion about what you do first and what you do second.
Sure. And I mean, if you're totally new to this and you're following along and you still have to do it one step at a time, that's totally cool. Because only after you really get the swing of it will you start combining steps.
Right. And it's also kind of important to remind our viewers that if this did confuse you, watch it 2, 3 times.
Yeah, just go back and review it. Because really we could sit here and just kind of, beat the dead horse over and over like we do in math class, but you do have the liberty of rewinding us and going back and listening to what we said. And so far, everything has been pretty clear.
Yeah, I think so too.
I've picked it up.
So I'll clear our Photoshop screen.
I'm not even a math guy.
Jump back to PowerPoint.
Yay, PowerPoint.
And jump to the next slide.
Advanced matrix operations. That's it. The other half of the audience just left the room.
No, they just passed out unconscious.
Yeah. All right, well, what do we got?
Okay, well, there's many advanced matrix operations. We're going to be talking only about one of them.
Okay.
It's called a determinant.
Ooh.
Determinants can be taken they can only be taken for square matrices.
Okay.
This means matrices with the same number of rows and columns.
Okay, that makes sense. That would make it square.
Taking determinants for 2 by 2, so 2 row by 2 row, and 3 by 3, 3 row by 3 row matrices is very easy. For higher level ones, so let's say 4 by 4, 5 by 5.
Sure.
It gets
18 by 18?
You could. I'm not going to do it. It would take like half an hour.
Gotcha.
But it can be done. It just becomes a little more challenging.
Sure.
In any case, for now, all we care about is whether the determinant is equal to 0. Because essentially, what the determinant will tell you whether or not one row is telling you stuff you already knew.
Oh, okay.
So if a determinant is 0, that basically means you can't solve for all your variables.
Because you're repeating information.
Right, exactly.
Right.
So that's where this becomes important.
So when you have 2 rows in a matrix that are basically saying the same thing in different ways, that doesn't help you at all.
Right. It's the same thing like saying, let's say I told you x plus y plus z is 5. 2x plus 2y plus 2z is 10.
Sure.
all I did was multiply it by 2. I'm not giving you new information.
You don't have anywhere new to go. In a way, if you think this might be a little bit far-fetched, but I'm a 3D guy. To me, that's a lot like triangulation. You need 3 separate points at least to get all these areas. If you only get 2, you're not going to get all the information.
Right. Well, if you're dealing with 3 variables.
Exactly.
If you're dealing with 4 variables, you need 4 separate
Yeah, then you need 4. There you go. So that'd be quadrangulation. Ooh. All right, keep going.
Fancy vocab. Quadrangulation? Isn't that
quadrangulation.
Oh, quadrangulation. Okay, fine. I agree.
Yeah.
Basic matrix operations may change the value of your determinant, but not whether it is equal to 0.
Ah.
So, essentially, what I'm trying to say there is that your determinant is going to be a number. Let's say 18.
Mm-hmm.
By doing operations, the 3 we just talked about, the adding 2 rows or multiplying a row by a constant or swapping 2 rows, you'll change the value of the determinant. So if it was 18, it might become 16.
Okay.
But you won't change... Well, okay, yeah, it might become 16, but you won't change... It won't become 0.
Okay. It's either going to be 0 or it's not, no matter what you do.
So essentially, the 3 operations affected as follows. Adding 2 rows, surprisingly, doesn't change the determinant.
Okay.
So it stays the same. Swapping 2 rows changes the sign of the determinant.
Makes it from positive to negative.
Or vice versa.
Yeah.
So 5 becomes negative 5.
Mm-hmm.
And multiplying a row by a constant multiplies the determinant by the same constant.
Okay, cool.
So if you multiply a row by 3, the determinant gets multiplied by 3.
That makes sense. I'm with you.
So you might want to jot those down because they're not in the PowerPoint.
Mm-hmm.
And just keep that in mind. So taking a 2 by 2 determinant. That's really easy. Let's say you had a matrix with 4 values, A, B, C, and D.
Mm-hmm.
The determinant is simply A times D diagonally minus B times C diagonally. So in this example here, you go 1 times 4 minus 2 times 3, which is 4 minus 6, which is negative 2.
Gotcha.
Very simple.
Yeah.
A 3 by 3 determinant looks complicated if you only look at the top of the slide. Heck, it probably looks complicated if you look at the bottom of the slide with all the arrows.
Yeah, it looks a little scary.
But it's really quite simple. What you do is, this is going to be, well, I should say this is going to be what it ends up being, but no one ever remembers that.
Right.
I don't even remember that.
Yeah.
What you do is, you take your square matrix, and you write these first 2 rows again at the end.
Okay.
So you see how this goes A, B, C, A, B.
Mm-hmm.
D, E, F, D, E, etc. Mm-hmm. And then as you go down diagonally, the first 3, those get added. So D times E times I is added. See, D times E times I plus the next diagonal, B times F times G.
You might actually draw lines to that because it's going to be really hard to track your
cursor.
Yeah.
Okay, so if you're going diagonally,
yeah,
A times E times I gets added. B times F times G gets added. Mm-hmm. C times D times H gets added. Mm-hmm. So those 3 get added. Those are the ones in black on the bottom right.
On the right side here.
Meanwhile, if you're going up from the diagonal, up diagonally, those get subtracted. So G times E times C is subtracted. Mm-hmm. H times F times A is subtracted. I times D times B is subtracted.
I gotcha.
So the ones going up in green are subtracted.
Right.
So as you can see, I said you add on the top. I say you add these 3, and then these 3 you add them, but you subtract in front.
Subtract the whole.
So you can subtract them individually or calculate it and then subtract the whole.
Yeah.
It doesn't matter.
That makes sense. Cool.
So it seems very complicated, but I have an example. So here's our matrix. 1 times 2 times 3, 4 times 5 times 6, 7 times 8 times 9. And then I wrote it out with the first 2 columns we've written a second time.
Sure.
And now what you do is you go down diagonally. 1 times 5 times 9. That's right here. 1 times 5 times 9. And that's 45 if you look right below it.
Right.
And I take the next diagonal. 2 times 6 times 7. And that's 84 if you look at the bottom of the slide. And I do it again for 3 times 4 times 8. So that ends up being 225 if you add these 3 components.
Sure.
225.
Right.
Then, if you go the other way, up, 7 times 5 times 3 is 105. 8 times 6 times 1 is 48. 9 times 4 times 2 is 72. I added those 3 and then I subtracted the whole. You could also, like I said, subtract each individual component.
Sure.
And you get minus 225. And that's 0.
Now, if you get a 0 as your determinant, again, what does that mean?
It means that one of your rows, at least one of your rows, is telling you the same thing as some combination of your other rows. I'll explain in Photoshop.
Okay, cool.
So what we're saying here is that there is some redundancy in 1, 2, 3, 4, 5, 6, 7, 8, 9.
That's the word I was looking for. There's redundancy in there.
So I'll show it in Photoshop. We have our matrix.
Mhm.
1, 2, 3, 4, 5, 6, 7, 8, 9. So that's our matrix. Let's say we take 2 times row 2. I'll write it over here. You get 1, 2, 3, 8, 10, 12, 7, 8, 9. Can you see the redundancy, Zach?
Actually, not right off the top of my head. Wait a minute. Hang on. It's coming to me. Yeah, it's 1 and 3, isn't it?
Row 2 minus row 1.
Oh, okay. Never mind.
That'll give you row 3.
Oh, okay.
So if you do that, you're going to get 1, 2, 3. 8 minus 1 is 7.
Yeah.
10 minus 2 is 8. And 12 minus 3 is 9.
Right.
And then you have
get
7,
8, 9 at
9.
the bottom. Gotcha.
So you have 2 rows that are essentially saying the exact same thing right now.
Yeah.
And therefore, that doesn't help you. You can't solve for X, Y, and Z should that happen.
Gotcha.
So
Basically, you need more information.
right, or let's say or you need different information. Let's say instead of 7, 8, 9, it was 7, 8, 8. That would work.
You could you could do something with that.
Right, that would work. So, that's how you do a 3 by 3 determinant.
Cool.
When you get to greater order determinants, say a 4 by 4, it gets really complicated if you don't understand right now. If you don't understand what we covered before,
Rewind.
rewind,
Go back.
because you need that to solve 4 by 4, 5 by 5, etc.
Sure.
The important thing to remember are those 3 points I said earlier. Adding 2 rows doesn't change the value of your determinant. Multiplying a row by a constant multiplies the determinant by the same constant.
Sure.
And swapping 2 rows changes the sign. Those are very important to remember because what you have to do is break your determinant down, let's say a 4 by 4, into 4 3 by 3 determinants. And I'll explain how you do that. It's called expanding along a row or expanding along a column. You could do either, and neither changes the value of the determinant.
Okay.
So the goal is to get a row or a column using the operations with as many zeros as possible. Because as you can see, in the final result, you'll have something like constant times determinant, plus constant times determinant, minus constant times determinant. So if you can get those constants to be 0, you suddenly don't have to calculate those determinants.
Right.
It doesn't matter. So, in this case, what I did is I expanded along this column here, the one I'm circling, or ovaling.
Close enough.
And then I said, okay, so if I look at A2, which is the first value in the column, you ignore the row and the column that A2 is on. So you ignore both the row and this column that is circled or ovaled. And then you say, wait, I've got, not in ovals now, I have 9 values.
Right.
Those form the 3 by 3 determinant.
Okay.
So you'll see B1, B3, B4, and etc. The only other thing to know is how to calculate the sign of whatever A2 was. Let's say A2 was 5. The important thing to know is whether you go 5 times determinant or negative whatever that value was times determinant.
And how do you know that?
Well, you kind of read it like a checkerboard. So you imagine the top square here is positive.
Right.
And anything to its left or right, anything to its horizontal or vertical.
Anything adjacent to it?
Not adjacent, because the diagonal.
Oh, well.
But anything to its horizontal movement or vertical movement is the opposite sign.
Right.
Kind of like how a checkerboard alternates between black and white tiles.
I'm with you. So A2 would be negative.
Didn't mean to do that. I'm sorry.
That's okay.
So A1 is positive. A2 is negative. B2 is positive. B3 is negative. If you follow, I went like that. You kind of hard to see the arrows. Then down there, and then across there. And that's horribly drawn. In any case, I'll grab the eraser tool, or erase all ink on slide, and we'll continue. So if you use the checkerboard methodology, you'll see that A2 is negative.
Sure.
So it's negative A2 times the determinant of that you had. But
so
like
you'd have to solve a determinant using B1, 3, and 4, and C1, 3, 4, and so on.
Right.
Gotcha.
So, like I said, we're expanding along this column, and then you go to the next entry. You ignore this row this time.
Right.
And you follow the same technique. So you have a new 3 by 3 determinant, as you can see, whatever is not circled. And then you have to know what B2 is.
Gotcha.
And B2 happens to be positive.
Right.
and so on and so forth. But if you remember how each of those operations alters the determinant, then it's very easy to get a whole bunch of the final equations, these down here, to be 0. Like you can get, let's say, D2 to be 0, and then you don't have to do this whole thing.
Right.
And you'll get, let's say, C2 to be 0, and you don't have to do this whole thing. So what you start by doing is doing as much reduction to the 4x4 matrix as you can.
Sure.
And you say, look, the determinant is going to be something. And each of these steps is affecting it this way. And then you keep track of all that, and you can solve your 4x4 determinant easily.
I gotcha. That's pretty in-depth, but you can definitely follow it.
Right. So, but all of this, for those of you who are panicking, is outside the scope of this VTM. You don't have to understand this to follow the rest of it.
Sure.
We're not really dealing with 4-variable equations.
Right.
So don't worry if you didn't really understand that. Consider that for your culture.
But actually, again, I'm not the math guy. I'm here kind of as a guest to help Demondo kind of keep things moving and happy. But I was able to follow that. So I think if you're a little bit lost, go back and rewind. Make sure that you paid really close attention to solving the 3x3 matrices. And I don't think you should have a problem with this. Right.
And if you thought about it, if you applied the same technique of reduction of order,
right.
So you turn the same way you turn a 4x4 into into 4 3x3s.
Right.
You can turn a 3x3 into 3 2x2s, and it would work out the same.
Yep.
The value of the determinant doing that doesn't change.
Cool.
Okay, so with all that said and done, we can finally get into Cramer's rule.
Ooh.
Cramer's rule uses determinants, but it lets you solve pretty much immediately if the determinant is easy to calculate for any variable. So you don't have to do all the work to solve for x. You can say, what is x, and use Cramer's rule to solve x.
Cool.
So, ideally, Cramer's rule allows you to quickly solve for any variable in a system of linear equations. The reason I said ideally is, let's say you had 5 variables. Suddenly you don't want to be doing determinants.
Right. It's going to take a while.
Well, it might not, but depending on the setup, it might take a while.
Sure.
So then the next point is first isolate and take the determinant of the coefficient matrix. If you recall, those are the coefficients x, y, and z.
Right.
So you take that determinant. I'm calling that value D. You can call it whatever you want. You can call it Jimmy.
We'll stick with D.
Okay, then, let's say you want to solve for x. You plug in the answer column, which was that column after the vertical line,
sure,
into the column that represented x. And you take that determinant. We'll call that A.
Right.
And if you take this division, A divided by D, because don't forget the determinant is just a number, that's equal to what your variable is equal to.
Cool. Do you have an example?
No, but yes, I do. So essentially, these are the examples from the previous slide, from the previous lesson. You could try these, but if you want to see an example of Cramer's rule, stay tuned because I didn't realize this was the next slide. I'm going to jump into Photoshop and do the same example we did before. The 1, 1, 2, 3. I'll show you in Photoshop.
Just show me.
Okay, so here is our old matrix.
All right.
1, 2, 3, 3. 4, 5, 6, 6. 7, 8, 8, 2.
All right.
So instead of putting the vertical line like I normally do, I'll break off the coefficient matrix and call this a second, 3-row by 1-column matrix.
Okay, fair enough.
So this is the solution matrix, sol matrix. And this here is the coefficient matrix. Coefficient. I can spell.
I believe you.
Matrix. So like I said, you start by getting the determinant of the coefficient matrix. So that's 1 times 5 times 8, which is 40, right? 5 times 8 is 40, and times 1 is nothing, so 40, plus, you know what, I'm going to write it out just to follow convention.
Do it. Show us.
2, 5, 8, 3, 6, 8, 1, 4, 7, 2, 5, 8.
Yeah.
And like I said, this isn't necessarily standard notation, it's my notation.
Cool.
So we calculated that to be 40. So now we do 6 times 7 is 42, times 2 is 84, so plus 84. Then you do this, so 3 times 4 is 12, times 8 is 96, I believe. So plus 96. And then you have the whole, so we calculate all this.
Yep.
We have to subtract whatever's after that. And that's 7 times 5 times 3.
105.
105. Plus, because you're going to minus the whole thing. 8 times 6 times 1 is 48.
Mm-hmm.
And 8 times 4 times 2 is 8 times 8, which is 64. And if you calculate this whole thing, I believe you get 3.
Well, there you go.
So, 3.
So that's the value. That's D, isn't it?
That was A.
That's
No, I called that D.
Yeah, you did call that D. See, I was paying attention.
You
man.
were paying attention. You're paying more attention than the teacher was. So I'm just going to clear that and just write D equals 3.
Gotcha.
So
Cool.
you don't have to have this whole mess on the screen.
Yay.
So D equals 3.
Mm-hmm.
That's important. And
Now we have to find A.
Right, we're only going to solve for X because we already solved for the other two.
Sure.
So, okay, solving for X. We have our matrix, a coefficient matrix. 1, 2, 3, 4, 5, 6, 7, 8, 8.
Mm-hmm.
We also had our solution matrix, which was, I think, what was it? Do you remember, Zach?
No, I don't. I have no
3, 6, 2.
clue. Good enough.
Good enough. If it doesn't match up, then...
We're going to plug the solution into the X column.
Right, into the first column, which was X.
Right.
So your new matrix is 3, 6, 2, 2, 5, 8,
Mm-hmm.
3, 6, 8. So we've already done a whole bunch of 3 by 3 determinants. Should we do another one, or do you think...
Just one more won't hurt us. Come on.
Okay. So, 3 times 5 times 8 is 40 times 3, which is 120.
Mm-hmm.
Okay, I'm going to actually erase and do the convention just because it's also easier for me to work with.
Yeah, I was doing the wraparound in my head, but I wasn't sure if you wanted to do that.
So it's 3, 2, 6, 5, 2, 8. I'm not going to erase that 120, I'm just going to scribble it out.
Okay.
Right over here.
Flipping
120.
that pen over.
Well, I find the eraser tool is pretty big, and I'm too lazy to resize an eraser.
With you.
So this, I calculated was 120.
Uh-huh.
2 times 6 times 2 is 24. So, I'll write it over here, doesn't matter the order.
Right.
And 3 times 6 times 8 is 96 again.
Mm-hmm.
96? No.
No.
No, not 96.
That doesn't work out.
No, it doesn't, because that value changed.
Yeah, it's 48 times 3, which is... Oh, now...
128, possibly? 40, I'll just grab my Texas Instrument.
Do it on TI. We both have slow brains.
144.
We've been doing this all night. 144.
I was close, 148.
The answer is 144.
So I just said.
I'm just telling you, I figured it out in my head finally.
And the whole bunch of audience members are like screaming at the monitor. What's taking you so long? You need a calculator for that?
Yeah.
Okay, let me just double check to make sure that's right. Yeah.
Looks good.
Okay, now you go the other way. So 2 times 5 times 3 is 30.
Mm-hmm.
So you have a big minus. And you have 30.
Mm-hmm.
That's supposed to be right there. So 8 times 6 times 3.
It helps to draw your matrices a little straighter than Demondo's.
Yeah, it does. As I was saying, 8 times 6 times 3 is the same answer we got last time, which is 144.
Yep.
Wrong
end of the pen, buddy.
Wrong end of the pen. What was that, 30?
Yep, that was 30.
Plus 144.
Mm-hmm.
Plus 8 times 6 times 2, which is 96 this time. 12 times 8 is 96. And if you work all that out, you'll get A is equal to 18. I hope.
Okay.
In any
enough.
case, you have A is equal to 18 and D is equal to 3.
Gotcha. So now you just divide the two.
Right, so I'll just clear this all out.
Uh-huh.
A is equal to 18 as we had.
Mm-hmm. And D is equal to 3.
Equal to 3. And I believe we said that you do A divided by D.
Mm-hmm.
Equals
would be
18
6.
divided by 3, which is 6. So we said
of x is now...
the value of x is now 6. So if you had to solve for all 3 variables, you might find this method isn't faster.
Sure.
It depends what you're solving for.
Yeah.
But if you're only solving for 1...
This could be a really quick way to get it done.
Right. And I believe 6 was what we got the first time.
Yeah.
So there you go. And as I accidentally jumped to the slide prior, these are the examples we did in the end of lesson 2.
So try giving those a go using some of the things you've learned from this lesson.
Yeah, these 2 new methods.
Absolutely. So... excellent work, Demondo. That is going to, unless you have anything else to add.
I'm just trying to think. Like I said, Cramer's rule requires that the first determinant, the d value, is not 0.
Right.
But if it was 0, you couldn't solve for all the variables anyway.
There you go. So that's going to wrap it up for this video. I'd like to thank Demondo for his excellent work.
Thank you, Zach.
And thanks to you guys for watching. And that's it.
Thanks a lot.